The secant value of pi over 6 is equal to 1 over x. So it's 1 over radical 3 over 2. So, of course, that's equal to 2 over radical 3. And in order for me to rationalize the denominator, I have to multiply top and bottom by the square root of 3 over the square root of 3. So that's going to equal 2 square roots of 3 over 3. And then finally, for my cotangent of pi over 6, that's equal to x over y. X is equal to the square root of 3 over 2, and y is equal to 1/2. I can cancel out my 2's, and that leaves me with square root of 3 over 1, which of course is just the square root of 3. All right, that's how you find the 6 trig functions using the new circular definitions of, in this case, one of the special angles. One of the most important tools to have in the trigonometric solution toolbox is the unit circle showing all of the special angles, written in both degrees and radian values, and then the corresponding arc length, the S values. Let's look at the complete unit circle, and we'll use it to solve some trigonometric functions. So here's our unit circle, and you can see that the problem we just did would have been, if I were to draw this angle theta, and we said it was pi over 6, which would have been the equivalent of 30 degrees, and you can see that the point should be labeled as we had done. Now, we can look at the other points on this circle, for instance, pi over 4, which is the equivalent of 45 degrees, and here would be my x comma y value. 60 degrees is the same as pi over 3, and what I want to point out to you is the relationship between these two points. Remember that 60 degrees and 30 degrees are complementary, and that they appear in the same right triangle. And notice that the x and y values have simply been interchanged here. So they have the same actual numerical values, but the x and y's have been interchanged. What I then want you to notice is, regardless of where else you go on this unit circle, you will find those same 3 values. When I say values, those same 3 points will be throughout the rest of the unit circle. So initially you would say, my goodness, there's a whole bunch of things that I need to memorize, and the answer is no, you don't have to memorize them. In fact, if you memorize just these 3 that are in the first quadrant, and then apply the idea of the sign SIGN, that is, we know that everything is positive for the trig values in the first quadrant, but in the second quadrant, we know that sine and cosecant, are positive, and we know that tangent and, of course, cotangent are positive here, and we know that cosine and secant are positive here. Then you can calculate the remaining values for each of the angles by using the 3 that you've memorized in the first quadrant and then applying the appropriate sign, SIGN, for those trigonometric functions. Okay, now what I want to do is use the unit circle in the next example to find the 6 circular functions of the given angles. Use the unit circle to find the exact values of cosine 7 pi over 4, sine 7 pi over 4, and tangent of negative 5 pi over 3. let's apply the circular functions to solve this particular problem. So what I want to do then is start by drawing 7 pi over 4. So that's a positive angle, and 7 pi over 4 lands me here. And actually, it's a little bit further along. Let me redraw that. It should be smack dab in the middle there. And what I know is if I would draw the unit circle on here, that this point would be square root of 2 over 2, comma, negative square root of 2 over 2. And so now, if I want the sine of 7 pi over 4, then what I'm looking for is the y value. And the y value is negative square root of 2 over 2. If I want to find the cosine of 7 pi over 4, then what I'm looking for is the x value. So cosine 7 pi over 4 equals the square root of 2 over 2. All right, the other problem that we were asked to do is to find the tangent of negative 5 pi over 3. So I need to redraw that, or draw that angle, because of course it's different than the 7 pi over 4. So for that angle, it's negative. So we go negative 5 pi over 3, and it's going to land approximately there. Negative 5 pi over 3. So therefore, if I draw my unit circle, this point is going to be labeled 1/2, comma, square root of 3 over 2. And therefore, if I want to find the tangent of negative 5 pi over 3, then that's going to be equal to the y value divided by the x value. So I will take the y value, square root of 3 over 2, divide that by the x value, 1/2. I can cancel out my 2's, and of course it all equals the square root of 3. All right, now let's apply the circular functions to solve application problems. Here's our first application problem. The average number of daylight hours at San Antonio, Texas, can be modeled by the equation f of x equals 1.95 cosine of the quantity pi over 6 times x minus 6.6 plus 12.15, where x equals 1 corresponds to January 1st, and where x equals 2 corresponds to February 1st, and then so on. Evaluate f of 7 and interpret the results. So I have the equation written up here. We want to evaluate f of 7. Make sure that your calculator is in radian mode, because that's what we're dealing with here, is radians. And now what we do is substitute 7 for the x. So we have 1.95 cosine pi over 6 times 7 minus 6.6 plus 12.15. Plugging all of that into your calculator and multiplying it out, plugging it into the calculator, you'll find that f of 7 is going to be equal to 14.06. But what does that really mean, the 14.06? What it means is that we're looking at f of 7. f of 7 refers to the 7th month, in other words, July 1st. So on July 1st, there would be slightly more than 14 hours of daylight. Okay, well, now that I've done an application problem, I would like to give you the opportunity to solve an application problem using the circular functions on your own.